Welcome, everyone. We'll get back to the hockey stick identity, which will become relevant, surprisingly. Course announcements. Office hours are, as usual, right after class today. I encourage everyone who is interested to just stick around and chat, even if you don't have any questions specifically about the problem set that was passed or anything in lecture, though feel free to ask those questions as well. Problem set 3 grades are out. Let Vincent and me know if you think that something should be reconsidered. Are there any questions? Is Wednesday a holiday? I don't think it is a holiday in Quebec. So it's not a holiday for McGill. If you have issues making Wednesday, let me know. Okay, any more questions? Cool. Let's go on. So today we'll be talking about binary search trees. So in a binary tree, I realize this is sort of notation that I haven't necessarily defined yet. We said that the left subtree of a node is the left child plus the rest of the entire portion of the tree that's rooted at that left child. Likewise, for the right subtree, it's the entire big branch of the tree. I mean, you have a tree and you have two branches coming off the left subtree and a right subtree, depending on left subtree and right subtree. So a binary search tree is a binary tree with each node storing a key. So here, these are some nodes in a binary tree. So for example, the left subtree of the node with a 6, was storing the key 6, is this whole thing. This is the left subtree of the node with key 6, and this is the right subtree of the node with key 6. Okay, so in a binary search tree, we require specifically that for every node v, the left subtree has all nodes storing keys, I guess I should say, has all nodes storing keys less than or equal to the key at v. And the right subtree has all the nodes storing keys greater than or equal to that of v. So here we have 6. All the keys here are less than 6. All the keys here are greater than or equal to 6. Likewise with 15, everything on the left subtree has all the nodes storing keys less than 15, has all the, on the right-hand subtree, everything is greater than 15, or equal to, less than or equal to, or greater than or equal to. Are there any questions about this? So can there be more than one binary tree for a given set of keys? Sorry, I guess I should say binary search tree. Can there be more than one binary search tree for a given set of keys? As an example, okay. Are binary search trees only defined for integers? For integer keys, no. The keys could be anything. Yes, there could be more than one. There could be a lot of different ones. Yes. So here's an example. Here we have 6 as the root of the binary search tree. And everything over here is less than 6. Everything over here is greater than 6. Here we actually have 2 keys which are the same, which is perfectly fine. But even if you don't have keys being the same, you can still have very different topologies for the binary search tree. It doesn't have to be balanced, as there is a comment. Indeed, it doesn't have to be balanced. This is another binary search tree with the same keys. Here the root is 2, and it doesn't even have a left subtree. It just has a right subtree because everything is greater than or equal to 2. And this is just another way of arranging those keys. Are there any questions? So in storing a binary search tree, we generally store at each node the key, pointers to the left and right children, or if they don't exist, then we can just store something that tells us that they don't exist, and a pointer to the parent. So this just allows us to move around the tree. We can say, okay, given that I am at a node, I know that I can immediately get to either its children or the parent, or I can work out what the key is at that node. Okay. So we will want the following operations within a binary search tree specifically. Search, that's why it's called a binary search tree. Find if a given key is in that tree. Maximum and minimum, find the maximum and minimum keys within the tree. Successor and predecessor. Given the keys, given a tree and a particular key in the tree, find the keys immediately greater and less than it. So the one that is larger than it, but the smallest one larger than it, and the largest one smaller than it. That would be useful if we're trying to sort of go through the keys in order within the tree. Insert or delete, we want to be able to remove or add a new key to the tree. Any questions about these? So this will sort of, this might feel familiar. These are slightly different operations than we were looking at with heaps, but there are some similarities. And this is a data structure which we want to have these various operations, and we want to be able to do them efficiently. Cool. So let's start out with search. Suppose we're given a value k in a binary search tree. How can we check if k is stored in the tree? Suppose I were trying to find out if 10 is in my tree. You can traverse the tree. You could just literally, you could go through literally every key in the tree. We'd like to do this a bit faster than looking at everything in the tree. Yeah. So we can use the property of the binary search tree where we can say, okay, suppose I'm looking for key k. If the root has key kx, then I know that I'll be in the left subtree if k is less than kx. And I know I'll be in the right subtree if k is greater than kx. So I immediately get to subdivide, not necessarily cut things in half because it's not necessarily balanced, but can cut things into the left side and the right side. So I go over here if I'm looking for 10. Is it bigger or less than 6? Well, it's bigger than 6, so I go down to the right subtree here. Is it bigger than 7 or less than 7? It's bigger than 7, so I go down to the right subtree here. Less than 13, so I go over here. Is 10 here? This is my last node. I don't have anything more to do, so I say, okay, 10 is not here. But if it were here, it would be down here. We stop if we ever find the key that we're looking for, or if there isn't a left or a right child to move to. How long does this take? So we don't know what the height of the tree is. So the word height of a tree, we previously used the word depth, which is how many edges are there from a node to the root. So this is a node at depth 2, this is a node at depth 3 and 4 and so on. The height of the tree is just the maximum depth of all of the nodes. It's sort of weird to think of height being like the same as depth, but yeah, so the height of the tree is just the maximum depth of the nodes. And so we might have to go down the full height of the tree. Now, if the tree is balanced, we were looking at heaps, which are balanced, then the height of the tree is going to be log n, but it might not be log n, it might be n, or order of n. So we're going to write it just down as O of h. So it'll take time linear in the height of the tree, whatever that is. Maximum and minimum. How do we find the max key in a tree? Rightmost. Keep on going right. Keep going right in the tree until it's not possible anymore. Yep, exactly. Go right from the root, right down here, and oh, we're done. 20, that's the max. Similarly with the min, we just go left. Down, down, down. It's because going to the left just means we take the lowest, the lower of the subtrees, and then find the lower subtree within that, and so on. How long does this take? O of h, where h is the height. For the record, if you wrote O of n, or big O of n, that would not be wrong. It would just, because it is certainly big O of n, but I'm trying to be a little bit more strict than that. Sometimes h is less than n. Also, for the record, if you write at most big O of h, that is redundant because big O of h is already an at most. So you could write a big O of h is equivalent to writing at most theta of h, basically. Okay. That's just like clarification on big O notation. But yeah, again, it is big O of h where h is the height. Okay, now let's get into slightly more complicated territory, successor and predecessor. Given a node with key kv, how to find the successor w to v, that is the smallest key that is larger than kv. Let's just assume for the sake of simplicity that all keys are different. So how would I find the successor to, for example, 6? Or the successor to 7? What are people's thoughts? How would I find the successor to 4? So the successor to 4 is going to be 6, for example. The successor to 7 is going to be 9. Successor to 6 is going to be 7. So what is the rule that we can use to find where that thing is? So if we're at 4, how do we get to 6? How do we know what 6 should be? If we're at if we are at 7, how do we know what the successor should be, which is 9? If we're at 9, how do we know what the successor should be, which is 13? If we're at 13, then how do we know the successor is 15? Do we need to backtrack? We may need to backtrack. We may need to, as it were, forward track. There's a suggestion about finding the, about looking at the smallest key in the right subtree. But there's also a suggestion about looking at parents of parents, ancestors. So in the case of 15, it makes sense that we need to find something that's greater than 15. So we're going to have to look in this subtree. And then we want to find the thing that's smallest out of this subtree. So we just find the minimum element of the subtree, which is the leftmost element. But 15 might have not have had a right subtree. So in that case, what are we going to do? Well, if we are looking, for example, at 13, which doesn't have a right subtree, we're going to have to go up to find it. And then that sort of raises the question of how did we know we had to go to the right subtree at all? Why couldn't we have gone, maybe if, maybe instead of finding the successor to 7 down here in the right subtree of 7, maybe there could have been something up here, which was the successor to 7. So let's make this a little bit more rigorous. So any two nodes in the tree have a lowest common ancestor, which is the deepest node in the tree that is an ancestor of them both. So for example, 4 and 9 have the lowest common ancestor of 6. That is it's just like, if you go up, if you do the parent of 4 sometimes and parent of 9 sometimes, you get a node that is an ancestor. So an ancestor is just like something further up in the tree, or a parent of parents. That is a common ancestor of them both, and the lowest one. So 15 is a common ancestor of them both, but it's not the lowest one. 6 is the common ancestor. There's the lowest common ancestor. Okay. So let X be the LCA for V and W. We don't know where W is yet. So V and W must be on different subtrees from X, since it's the lowest common ancestor. Like the lowest common ancestor will always have the two things on different subtrees, because if they were on the same subtree, then you could just go down there. Is V on the left or the right subtree of X? Why can't it be on the right subtree? V has to be on the left subtree and W on the right because KV is less than KW. We know that we're trying to find W, which is the successor. So the key has to be greater. And since everything on the left subtree is smaller than everything on the right subtree, we have to have V on the left subtree and W on the right subtree, because they're in different subtrees. Okay. But then we have that the key of V is less than the key of X is less than the key of W. So W, it can't be the successor to V because X is between them. Wait, what? What happened? Where did we mess up? again, what we did was we took a node and we took its successor node, so the node with the immediately following key, and we looked at their common ancestor, their lowest common ancestor. And we said that, well, the lowest common ancestor, we always have to have we have to have V and W be on different subtrees. So V is on the left, W has to be on the right. What could be the case? Do they actually have to be on different subtrees? Ah, yes. So X could be V or W. V or W could be an ancestor of the other one. So for example, 7 and 9. 9 is W, 7 is V. V is an ancestor of W. So the least common ancestor, X, could be one of V and W. And in fact, what this logic says is that it has to be one of V or W. If there were anything that weren't V or W, then V would have to be on the left subtree, and W would have to be on the right subtree. And X would have a key between V and W. Does that make sense? So X equals V or W, so one of V or W is an ancestor of the other one. Like 7 is an ancestor of 9, 13 is an ancestor, 7 is an ancestor of 9, so 7, the successor, is 9 here. What is the successor of 9? 9 successor is 13, and 13 is an ancestor of 9. What is the successor of 13? It's 15. Well, 15 is an ancestor of 13. We don't know which way around it is. Sometimes you find the successor and it's below you. Sometimes it's above you, but it's either above, straight above, or straight below you. Questions? Okay, so case 1, X is V. So V is an ancestor to W. What is W here? People were suggesting it before. How do you find W? For example, if you're finding a successor to 7, how would you find the successor to 7 or the successor to 15? Go down the right subtree. And where is it in the right subtree? It's the leftmost node in the right subtree. So here, 15, you go right, but then immediately you keep on going left. 17. That's because it's the minimum of the right subtree. Because everything in the right subtree is bigger than 15. And so we need to find the minimum of the right subtree. This is just making our analysis from before a little bit more rigorous, because we felt like we had to go down the right subtree. We weren't absolutely sure that there wasn't something higher up in the tree that we had to consider. So case 2, X equals W. So W is the ancestor of V. So for example, here, 13, if we want to find the successor of 13, 13 doesn't have a right subtree. So we have to look up. And in this case, we look all the way up to 15. So what is W? How do you find W here? Which one of the ancestors is W? It's the first one, such that you are on the left-hand side of it. alternatively, it's the first one, which is just greater than v. So if you're at 13, you keep on going up. You're like, OK, 7, 6, those are both smaller. 15, that's bigger. Great, done. Now, this corresponds to 7, you were on the right-hand side. 6, you were on the right-hand side. 15, you were finally on the left-hand side. So you know that everything in this left tree is less than 15. So you know that you are now less than 15. So these two things are equivalent. You go up until you find something greater than you, or you go up until you find something where you're on the left-hand branch. They're exactly equivalent. If you went up any higher, then you would have found, you would either, no, it's not necessarily the same as reaching the root. So for example, 4, the successor is 6. So if I go up and I find 6, that's the successor. If I went up any higher, I would find something that is in this case larger than 6. But if I went one more the other way, suppose that the ancestor, the successor to 17 is 18. If I went higher, I would have found something that's actually less than 18. So either, if the parent of if I go up until I find something, the first thing which is larger than the key at v. If I go up any further, then I either become less than the key of v or I get even bigger. Here I would get less than the key of v, I would go to 15, and here I would get even bigger than the key of 4 here. Does this make sense? How do we know which case we're in? If there is no right subtree, yeah. If v has a right child, then we're in case 1. Otherwise, we're in case 2. I'll let you think about why that's the case. Are there any questions? Anything that's confusing here? On the previous slide, did we prove that the least common ancestor must be v or w? Yes, because if the least common ancestor were not v or w, then v would have to be on the left tree, w would have to be on the right tree, and the key of the least common ancestor would be between the keys of v and w. And so w couldn't be the successor. So this simplifies our analysis a lot. It basically says that v or w one of them has to be an ancestor of the other one. Because if one of them isn't the ancestor of the other one, then they have a least common ancestor which is different from them, and the key of the least common ancestor has to be between their keys. Essentially, yes. I didn't write this out as you would write a formal proof. I wrote this out as you might sort of explore it. But yes, this is a proof by contradiction. Suppose that that one of them is not the ancestor of the other. Then they have a least common ancestor, which is different from both of them. The least common ancestor's key has to be between their keys. Contradiction. Really good question. OK. And then again, we have an algorithm that runs in time O of h, because we're going, in this case, we're either going all the way up the tree, potentially, if we're trying to find ancestors, or we're going all the way down the tree if we're trying to find the minimum of the right subtree. So we either go up until we find the smallest ancestor on where you're on the left-hand side, or we go down until we find the minimum of the right subtree. But either way, it'll take time O of h. And then similar process for finding the predecessor. The predecessor is just, instead of the successor, it's the largest key that is smaller than the key you're currently at. And again, think about h as something we would really like to be log n. So if you were traversing the tree, finding successors, you would be doing a log n operation n times, which makes sense for doing something that is, reading things out in order. We've seen a lot of sorting algorithms that are n log n. Okay. How can we insert a new key into the binary search tree? We can do exactly the same thing that we were doing with search. We can search for where it would be if it were there, and then add it in exactly the place where it should be. So here, for example, if we're trying to add 13, we say, OK, it's bigger than 12, so we go down here. It's less than 18, so we go down here. It's less than 15. Oh, look, here's a nice space. Well, if there'd been something here, like 12.5, we would go down there, and we would put it on the appropriate side of that thing. OK. We just go searching for it, and if it's not there, add it. This takes, again, time O of h. Questions? This is not true if the tree were balanced. Yes, if the tree were balanced, we would have a problem. We would have to rebalance the tree or other things like that. In this case, this is just a binary search tree, no balancing going on at all. OK. Let's try deleting a node in the tree. First, suppose the node doesn't have a left child. What do we do? We can just move the right subtree up, with its root taking the place of the node we just deleted. Similarly, if we're missing a right child. So here, if we have no left child, we just move this up. And because all of the conditions which we had for a binary search tree were that the entire subtree was less than or greater than something, they will still be satisfied. So if you were looking at the preceding element, the condition on the binary search tree was that the entire subtree here was less than or greater than the stuff up here. So that condition will still be satisfied. Unlike in a heap, where it was very local, we have entire conditions on subtrees. OK, same thing if it's on the right-hand side, by the way. OK, so that's very easy. But what if we have both left and right subtrees? We can try replacing z with a node in the right subtree. Let's just suppose we're doing it in the right subtree. It would work either way. But which one do we need to pick if we're sort of taking a node from the right subtree and moving it up there? The smallest node in the right subtree. Yeah, we want to pick the minimum in the right subtree since everything in the right subtree has keys bigger than or equal to the key at z. And so if we want to keep that property holding, the only way we can do that is to pick the smallest one, because then we will still have everything in the right subtree be bigger than or equal to the key. So here's how we can do that. Here's a sort of simpler case where it's the thing right below z that is the minimum of the right subtree, because it has no left subtree down here. In that case, we can just move this all up and keep the left subtree of z exactly intact, keep the right subtree of y exactly intact. You just deleted z, moved up here. And you see that that works because y is greater than z is greater than L. And so it's perfectly reasonable to put y here. Everything here is less than y. Everything here is greater than y. Great. But we can do pretty much the same thing if we just consider the minimum of this right subtree. The minimum of this right subtree is going to be somewhere down here on the left of the right subtree. It's going to be some y. And it cannot have a left subtree because it's the minimum of this right subtree of z. So what we need to do is we need to sort of do some surgery here. We can first imagine sort of chopping off the right subtree and first moving y up to the root of the subtree. And that works perfectly fine for this separate binary search tree here. And it's because y is the smallest element. And so we can easily move it up to the root because all we need to show is that everything over here is greater than y, which we know is the case. And we can do the same surgery that we did before. Knowing that y doesn't have a left child, we can just move x up to be y, the new y, as it were. So now we have this sort of separate two binary search trees, and all we have to do is fuse them. And that's very easy since y has no left subtree. We take out z. Z was the thing we needed to take out. And we just put y in there in its place. So the overall transformation is we've moved y up to z. Y was the minimum of the right subtree. We've moved the right subtree of y into the place of y over here. And that's it. Are there any questions about this? It's a bit of thorny surgery, but if you wrap your head around it, it's nothing particularly complicated. This basically is already a proof that it works. How long does this process take? So we don't, we might get really lucky and not have to do too much moving, but we might have to go all the way down to find this minimum in the right-hand subtree. And so it could be O of h time. I mean, it is definitely big O of h time, but it could be as bad as linear in h. OK. Now, we've seen a lot of different things. All of our algorithms are running in O of h time, so we better work out what h is. What is the maximum height with n keys? N. Or more properly, n minus 1. But yes. O of n. What is the minimum height? Log n. We'd be happy if it were big O of log n. That would be nice. So that's a big difference. We would appreciate all of our algorithms running in log n time. So next time we're going to consider how to sort of enforce it being log n, but now let's sort of consider a typical binary search tree in some sense and see what it is for a typical binary search tree. So, and there are different ways to define typical. And the way that let's consider it here is suppose that we inserted 1, 2, all the way up to n into a binary search tree in random order. And we're going to look at what the expected height is. As we have our insertion algorithms, we just like insert them in just some order, and we see what the expected height of the tree is. Some things we're going to need first. We're going to use this hockey stick identity, which if you arrived early was the teaser problem at the start of class. So how can we prove this hockey stick identity? Here's the graphical visualization of it. The idea is that this is Pascal's triangle. And the idea of the hockey stick identity is you take the things which are I plus k choose k for I equals 0. So this is 5 choose 5, 6 choose 5, 7 choose 5, 8 choose 5. You add them all together. 1 plus 6 plus 21 plus 56. That equals 84. If you can do that math fast enough. And 84 is, this was 5 choose 5, 6 choose 5, all the way up to 8 choose 5. Sorry, yes, all the way up to 8 choose 5. And this is 9 choose, not 5, but 6. It looks like a hockey stick. Here's a really short hockey stick. 1 plus 12 equals 13. And this is a reverse hockey stick, which is just the same as if we did, remember Pascal's triangle can be flipped across the side. So this is the same as this hockey stick here. Ding. 1 plus 7 plus 28 plus 84 plus 210 plus 462 plus 924 equals 1716, if you want to do the arithmetic. OK. How can we prove this? So it's similar to the problem on the homework, but it's not exactly the same. Does it always work? Yes, it always works. And yes, it's mind-blowing. It's super cool. It doesn't work on the edges. No, the hockey stick has to start on an edge. So you couldn't do like 1, 1, 1, 5. That's not going to work. But if you start on an edge, 1, 3, 6, 10, that works. 1, 10, 55, 66. 1 plus 10 plus 55 equals 66. So you have to always start on an edge, go down any amount you want, and then once you stop, you go across. But yeah, you can't just start in the middle of the tree. You have to start on the edge. That's why I starts out at 0 here. What's a general technique we might use for something like this? Induction. Great. Let's use induction. What is a good base case here? What should we even be inducting on here? could be inducting on n. We could do an induction on both of them at the same time, but let's just do an induction on n. What's a good base case if we're just inducting on n? We can do n equals 2. Go as small as you can, always, with your base case. What's the smallest thing that makes sense? Well, we have an n minus 1 here, so probably the smallest thing that makes sense is n equals 1. Let's use n equals 1 as our base case. This is the sum of one thing, and that one thing is k choose k, and that thing is equal to 1, and so it's definitely equal to the right-hand side, which is k plus 1, choose k plus 1. Great, our base case is done. Now suppose it's true for n equals m. So this is our inductive. This is the inductive hypothesis. So we're assuming this is true. How can we go from m to m plus 1? What is the thing we do to go from m to m plus 1? Yeah, in general, if you have a sum going up to m minus 1 and you're trying to make it a sum going up to m, well, you just add the thing. The thing is this term, m plus k choose k. You add it to both sides. We know that this is true because we assume this is true. We add m plus k choose k to both sides. On this side, it becomes the sum we want. On this side, we have the sum of these two things. Why is that true? Why is this? How can we simplify this? Pascal's identity. The thing in Pascal's triangle is exactly the two things summed together equal the thing below them. And what that means here is that m plus k choose k plus 1 plus m plus k choose k equals m plus 1 plus k choose k plus 1. And that's the end of our induction. We have now the identity that we wanted for n equals m plus 1. We're done. Questions about that? And geometrically or like graphically, what we're doing here is we're assuming that we got it for a hockey stick here, and we say, okay, what if we added this one? So we tried to make the hockey stick longer. Well, if we added this one, we know that this is the sum of these two things. So this plus this plus this plus this equals this. So this plus this plus this plus this plus this equals this plus this, which equals this. Isn't there a combinatorial argument as well? Yes, there is a combinatorial argument as well. I'll let you think about it. Question, why is it related to trees? We'll get to that. I think because of time constraints, we're going to have to get to it next time, but this will be important. The only other thing that we're going to need, I'm going to set up the proof for next time, but not actually do the proof. So we're going to use another form of Jensen's inequality. So we've seen the sort of the weighted form and the unweighted form, and here's another way of writing down the weighted form. If we have a convex function, then the expected value of f of x is greater than or equal to function of the expected value of x. This is basically the same as the weighted form of Jensen's inequality that we already saw. On the p set, we saw this weighted form of Jensen's inequality, which is just the sum of probabilities times or weights times f of x I is greater than or equal to the function applied to the weighted average. The weighted average of the function is greater than or equal to the function of the weighted average. But weighted averages are just expected values. So this is these are just basically the same thing. I mean, you have to worry about like, if you have infinitely many choices of xi and sort of like the limit. But yeah, basically, this is just the same as the thing we've already seen. If the pi are non-negative with the summing to 1. So we're going to use these two elements, this form of Jensen's inequality, and we're going to use the hockey stick identity to prove something cool next time. I will stick around for any questions, and there are office hours right after this. Thank you for coming.